So imagine a worker drops his wrench on a Tuesday afternoon. The air temperature is, only 82 degrees.
Which doesn't sound bad at all.
Right, exactly. The sky is slightly overcast. It's a completely unremarkable summer day. But within 45 minutes of dropping that wrench, this worker's internal organs just begin to systematically shut down.
The physiological collapse.
Exactly. His cognitive functions collapse, his skin gets dry and flush, and he just collapses right there on the concrete. And you have to ask, why? Because the thermometer on the local news, the one that told him it was a comfortable 82 degrees.
It essentially lied to him.
It totally lied. The ambient air temperature is only this tiny, tiny fraction of the thermodynamic reality surrounding us. So welcome back to QHSE Talks. Today we're basically tearing up the standard weather report.
We really are. Because the scenario you just described, it happens with terrifying frequency.
It does.
We hear a number like 82 degrees, and our brains just categorize it as safe.
Right.
Based purely on our casual everyday experiences.
Yeah, like going for a walk or whatever.
Right. But a job site is an entirely different thermodynamic ecosystem. When you introduce heavy physical exertion or radiant heat from machinery or, impermeable protective clothing.
Oh, the clothing is a huge factor.
Massive. Add in critical thresholds of humidity, and 82 degrees can absolutely become a lethal environment.
And that is the mission for this session. We are taking a really rigorous journey through Domain 1, Topic 6 from the Safety Professional Blueprint, which is calculating climate and environmental conditions.
It's a beast of a topic, but so crucial.
It really is. We're going to unpack ambient temperature, wind chill, the heat index, and just the actual physics of human survival. Because whether a crew is out there, laying asphalt in the middle of July.
Or repairing a comms tower in a sub-zero blizzard.
Exactly. Safety professionals cannot rely on subjective feelings or, standard weather apps on their phones. They have to rely on quantifiable physics to keep you and your teams alive.
Yeah, and to really understand why the math is so unforgiving here, we kind of have to establish a foundational premise about the human body itself.
Okay, let's hear it.
Well, we tend to think of ourselves as these incredibly adaptable creatures. And, in many ways we are. We live on every continent.
Right.
But biologically, internally, the human organism is effectively an engine with an alarmingly narrow operating band.
We are endotherms.
Yes, endotherms.
Yeah.
Our basal core temperature hovers right around 98.6 degrees Fahrenheit, or 37 degrees Celsius, and that number is not a preference.
No, it's a rule.
It is a strict biochemical requirement.
Right, because our bodies basically run on thousands of simultaneous chemical reactions, right? And the enzymes that trigger those reactions are shaped specifically to function at that exact temperature.
Exactly. They are highly specialized. If the core temperature drops by just a few degrees, those enzymes slow down.
They get sluggish.
Yeah, the metabolic machinery just grinds to a halt. And conversely, if the core temperature rises by just a few degrees, those enzymes begin to physically deform. They denature.
Which means the biological structures literally begin to unravel.
It's terrifying, honestly.
So we have this engine that must stay within a couple of degrees of 98.6 to survive. But the engine itself is constantly generating heat. Like if I am just sitting here in a chair, my resting metabolic rate is producing about 100 watts of heat energy.
You're an 100-watt fleshy light bulb.
I am a very fleshy light bulb.
And when a worker, say, picks up a sledgehammer or starts climbing scaffolding, that metabolic heat production skyrockets.
So what, like 500 watts?
Try 800, or even 1,000 watts of internal heat.
Oh, wow.
Yeah. And if the body cannot shed that excess heat into the surrounding environment, the core temperature is going to rise by about 1 degree Celsius every 5 to 7 minutes.
Wait, a degree every 5 minutes?
Literally. Left unchecked, that internal metabolic furnace will cause a fatal collapse in under an hour.
Which brings us to the constant, invisible battle happening right on the surface of our skin. We have to vent that heat. The environment has to absorb it.
But the environment is usually trying to push its own heat back into us.
Right. It's like a thermal bank account, isn't it? If withdrawals outpace deposits, you freeze. If deposits outpace withdrawals, you overheat. So how do we, as safety professionals, audit this thermal exchange?
Well, the exchange is governed by the basic laws of thermodynamics. The fundamental rule is that heat always flows from a higher temperature to a lower temperature, right? It's always attempting to reach equilibrium.
Right. Nature hates an imbalance.
Exactly. And this transfer happens through 4 distinct physical mechanisms. You've got conduction, convection, radiation, and evaporation.
Let's actually isolate these, because understanding the specific mechanism is like the only way a safety professional can implement a control. Conduction is probably the most intuitive one.
Yeah, conduction is just the transfer of heat through direct physical contact. On a molecular level, it's really just the vibration of atoms.
Bumping into each other.
Exactly. The atoms in a hotter object vibrate rapidly, and when they physically bump into the slower-moving atoms of a cooler object, they transfer that kinetic energy.
So if a worker kneels on a sun-baked steel deck, the rapidly vibrating iron atoms in that steel physically collide with the molecules in their work pants.
And that transfers the heat directly into their knees.
Yes. And the rate of that transfer depends heavily on the material, right? The thermal conductivity.
Oh, entirely. Steel is a fantastic conductor. Wood is not.
Which is why grabbing a steel wrench in freezing weather feels significantly colder than grabbing a wooden handle at the exact same temperature. The steel is just rapidly conducting the heat right out of your hand.
Precisely. It's stealing your heat. Then we have convection, which involves a medium that is actually moving.
Like wind.
Wind or even water. Convection requires a fluid, and in physics, gases like air count as fluids. So as air moves across your skin, it absorbs heat and carries it away.
But there's a boundary layer involved, right?
Yes. Your body naturally creates a tiny microscopic boundary layer of warmed air right next to your skin. It's like a tiny personal blanket.
I love that, a thermal blanket.
But when a breeze comes along, it physically displaces that warm boundary layer, replacing it with cooler air, which then absorbs more heat.
So this is basically the principle behind a desk fan. I mean, the fan doesn't actually lower the temperature of the room at all.
Not even a little bit.
It just mechanically accelerates the fluid dynamics, constantly stripping away our warm boundary layer.
Exactly.
Yeah.
You're just manually enforcing convection. Then we move to the third mechanism, which is radiation.
And this one can be deceptive, I think.
Very deceptive. Because it doesn't require direct contact, and it doesn't require a moving fluid. Actually, it doesn't require a medium at all. Radiation is the transfer of heat via electromagnetic waves.
Like infrared energy traveling from the sun through the literal vacuum of space right through our atmosphere and hitting a worker's hard hat.
Exactly. Photons of energy strike the object and excite its molecules, which generates heat.
On a job site, the sun is obviously the big one.
It is, but radiation is also just pouring off of asphalt or uninsulated steam pipes, molten metal in a foundry, even a large bank of high wattage work lights.
Oh yeah, those old halogen lights get insanely hot.
Right, and you can feel it. If you stand near a bonfire on a freezing night, your face feels incredibly hot while your back is freezing.
Right, because the air isn't hot.
Exactly. That heat on your face is purely radiant energy hitting your skin.
Okay, and then we arrive at the fourth mechanism, evaporation, which is essentially the human superpower. I mean, we are arguably the greatest evaporative coolers in the animal kingdom.
We really are. It is our primary survival mechanism against heat. And evaporation relies on the physics of phase change.
Turning a liquid into a gas.
Right. To turn liquid water into water vapor requires a massive input of energy, which we call the latent heat of vaporization.
So when sweat is excreted onto the skin, it requires energy to evaporate.
Yes, and it pulls that thermal energy directly from your body, leaving the remaining tissue much cooler.
But, and this is a massive but, evaporation has a fatal flaw, which goes back to the worker dropping the wrench in that 82-degree heat.
The humidity.
Right. If the surrounding air is already saturated with moisture, the sweat has literally nowhere to go.
That is what we call the vapor pressure deficit. If the air is highly humid, the vapor pressure of the atmosphere pushes back against the vapor pressure of the sweat on your skin.
It's like a traffic jam for water vapor.
That's a great way to put it. Evaporation slows to a crawl, or it just stops entirely. So the worker is still sweating profusely, losing critical water and electrolytes, but the sweat just rolls right off them.
They get zero cooling benefit.
None. They are essentially wearing a tight, insulating suit of hot water.
Okay, so as a safety professional, auditing this thermal bank account requires much more sophisticated tools than just a standard thermometer.
Oh, absolutely.
We have to measure the air, the radiant heat, and the evaporative potential. And we have, like, this alphabet soup of devices to do this. So let's start with DB, the dry bulb thermometer.
Right, so the dry bulb is your baseline. It measures the ambient air temperature, completely shielded from moisture, and completely shielded from any radiant heat.
Just standard air temp.
Just air. It tells you the convective potential of the air itself. Nothing more.
But as we just established, knowing the air temperature is nearly useless if we don't know if our sweat can actually evaporate. So how do we measure the humidity's impact on human cooling?
That requires the WB, the wet bulb thermometer. And it is really a brilliant piece of practical physics.
It's super old school but effective.
Very. It's a standard thermometer, but the bulb is enclosed in a wicking material, traditionally like a woven cotton sleeve, that is kept completely saturated with distilled water.
And then you pass a steady current of air over that wick.
Right.
Usually by using a sling psychrometer, where you literally spin it around in the air like a noisemaker, right? Or maybe a small battery-powered fan in the newer devices.
Yeah, the spinning is classic. So as the air passes over that wet cotton, the water evaporates, which pulls heat out of the thermometer bulb.
Because of that latent heat of vaporization we talked about.
Exactly. So the temperature reading on the wet bulb will actually drop until it reaches a state of thermodynamic equilibrium with the surrounding air's moisture content.
Okay, I want to make sure you, the listener, really grasp this dynamic. If I am in an arid desert, like in Arizona, the air is incredibly dry. When I spin that wet bulb, the water on the cotton wick is going to evaporate furiously.
Yes, very rapidly.
The latent heat of vaporization is going to suck the thermal energy right out of the thermometer, and that wet bulb reading is going to plunge significantly lower than the dry bulb air temperature.
And that plunging temperature on the wet bulb tells the safety manager that a worker's sweat will evaporate just as furiously.
Meaning the environment has a massive capacity for evaporative cooling.
Exactly. It's a safe zone for sweating.
But, and here's the flip side, if I take that exact same instrument into a swamp in Louisiana or, I don't know, deep inside a poorly ventilated paper mill where the air is just thick with steam.
Well, the air is already saturated. The water on the wick cannot evaporate. It just sits there.
Traffic jam.
Right. And without evaporation, there's no cooling effect. So the wet bulb thermometer will read almost exactly the same as the dry bulb thermometer.
Which proves that evaporative cooling has completely failed.
It's a major red flag.
Okay, so we have the air, we have the humidity. Now we need to capture that third threat, radiation. Yeah. For that, we use the GT, the globe temperature.
Also known as the Vernon globe thermometer.
Right. And what does it look like?
It consists of a standard temperature sensor placed precisely in the center of a hollow, thin-walled copper sphere that is painted matte black.
Okay, why black copper specifically? Why not just a regular metal probe?
Because black copper acts as an excellent approximation of a black body absorber.
Oh, like in physics class.
Exactly. It soaks in the electromagnetic radiation from the sun or the hot machinery or the asphalt. It basically mimics the way dark clothing or human skin would absorb that radiant energy.
That makes a lot of sense.
So the air inside that hollow sphere heats up, and the thermometer measures the combined effect of the ambient air and the radiant heat load.
So we have these three physical readings, but before we combine them, we need to address a mathematical quirk in the safety professional's toolbox.
The absolute scales.
Yeah. When we deal with deep thermodynamic equations, standard scales like Fahrenheit and Celsius suddenly become mathematically dangerous. Why do we need absolute temperature scales like Rankine or Kelvin?
Yeah. It really comes down to the fundamental definition of what temperature actually is.
Which is motion.
Right. Exactly. Temperature is a measurement of molecular kinetic energy, how fast the atoms are actually moving. Fahrenheit and Celsius are arbitrary, relative scales designed around the freezing and boiling points of water.
Which is convenient for making tea.
Right. But they allow for negative numbers.
Wait, if temperature is just a measurement of motion, how can you have negative motion?
You can't. You physically cannot. And that is the fatal flaw in relative scales.
So it breaks the math.
It completely breaks it. If you are running, say, an ideal gas law equation to calculate ventilation requirements for a confined space, and the winter air outside is negative 10 degrees Celsius, well, plugging a negative number into a multiplication or division equation will yield an impossible inverted physical state. You simply cannot calculate a negative volume of air.
It's just junk data at that point, so we have to shift the entire mathematical baseline so that zero actually means zero.
Exactly. We use absolute scales. Kelvin is the absolute scale for Celsius, and Rankine is the absolute scale for Fahrenheit.
So absolute 0 degrees Rankine is the theoretical point where all molecular vibration completely stops.
Right. There is no thermal energy left at all.
Yeah.
To convert Fahrenheit to Rankine, you just add roughly 460 degrees to the Fahrenheit reading.
So if a process oven is operating at, let's say, 320 degrees Fahrenheit, and we need to calculate its thermodynamic exhaust, we add 460.
Which gives us 780 degrees Rankine.
And we can now multiply and divide that number safely without violating the laws of physics.
Exactly. It ensures the math reflects reality. Now, speaking of reflecting reality, let's look at how safety professionals map the relationship between temperature and moisture.
Ah, the psychrometric chart.
Yes. This chart is notorious for looking like a chaotic spiderweb of intersecting lines, but it is actually a beautiful map of thermal physics.
It really is intimidating the first time you look at it. But let's trace a path on this map to find a really critical data point, the dew point.
Okay, let's do it.
Let's say a safety manager takes a reading. The dry bulb temperature is 60 degrees Fahrenheit, and the absolute moisture content in the air is measured at 80 grains of water vapor per pound of dry air.
How do we use the chart to predict danger here?
Okay, so you locate the dry bulb temperature of 60 degrees along the horizontal axis at the bottom.
Got it.
You draw a vertical line straight up. Then you find the moisture content, 80 grains on the vertical axis on the far right side. And you draw a horizontal line straight across to the left. So we basically follow those two lines until they intersect.
Right. And at the exact point where they intersect, you will find they hit this prominent curve forming the left boundary of the chart.
The saturation curve.
Exactly. That boundary line represents 100% relative humidity. If you follow the contour of that curve down to its temperature reading, you find the dew point.
That in this case is exactly 60 degrees.
Yes.
So what does that actually mean for the worker on the floor?
It means the air temperature and the dew point are identical. The air is physically incapable of holding another molecule of water vapor.
It's totally full.
Yep. Any further moisture introduced into the environment will immediately condense into liquid.
Condensation.
Right. So for the worker, it means their sweat is permanently trapped in a liquid state on their skin. Evaporation is dead.
That is a terrifying physiological state to be in. But, a safety manager can't constantly be cross-referencing charts and staring at 3 different thermometer dials while monitoring a massive construction site.
No, it's not practical.
We need a unified metric. And that brings us to the most important formula in environmental safety, the WBGT, or wet bulb globe temperature.
The gold standard. The WBGT was originally developed by the United States military back in the 1950s.
Really? I didn't know that.
Yeah, it was to reduce the devastating number of heat casualties occurring during basic training at Parris Island. They needed a single, actionable index that accounted for the total environmental heat stress.
So it's an index that takes our 3 thermometers and weights them based on their actual physiological impact on the human body.
Exactly.
Let's break down these formulas because there are 2 distinct calculations based on whether you are indoors or outdoors. Let's start with the indoor calculation, which the literature refers to as indoor or no solar load.
So the formula for an indoor environment is the WBGT equals 70% of the wet bulb reading plus 30% of the globe temperature reading.
Okay, I want to pause right here and play devil's advocate for a second.
Sure.
I am looking at an equation designed to calculate how hot a room is, right? And the standard air temperature, the dry bulb, is completely missing. How can an environmental temperature calculation completely ignore the actual air temperature?
I know, it feels like a mistake, doesn't it?
It really does.
But it actually reveals this profound truth about human thermoregulation. Think about it. When a worker is indoors, say deep inside a commercial laundry facility or a steel mill, there is no direct solar radiation.
No sun.
Right. The primary threats are the ambient humidity and the radiant heat radiating off the boilers or the furnaces.
So the wet bulb gets a massive 70% of the mathematical weight because evaporative cooling is doing 70% of the heavy lifting to keep that worker alive.
Precisely. If the humidity is low, the worker can survive incredible ambient heat indoors just by sweating it away.
That makes sense.
And then the globe temperature is given the remaining 30% to account for the physical objects radiating heat onto the worker.
So the convective heat transfer from this simple air temperature, the dry bulb, is so negligible compared to the power of evaporation and radiation in an enclosed space that the formula intentionally discards it, just to streamline the math.
Exactly. It's statistically insignificant indoors.
That makes profound biological sense. But what happens when that worker steps outside into a trench?
Outdoors, the environment changes. We introduce the sun. So the formula for outdoors with solar load shifts.
Okay, what's the new math?
The WBGT equals 70% of the wet bulb plus 20% of the globe temperature plus 10% of the dry bulb.
Oh, so the ambient air temperature makes a return, but only at a meager 10% weight.
Just 10.
The radiant globe drops slightly to 20%, But the wet bulb remains the absolute king at 70%.
Always. That 70% weight is basically a mathematical monument to human sweat.
I love that.
It's true. Regardless of whether you are in a dark boiler room or standing in the middle of a sun-baked highway, the ability of water to evaporate off your skin dictates your survival.
Let's talk about the real-world impact of this proportional weighting. Let's say a news anchor announces it is a scorching 95 degrees outside, but the humidity is incredibly low.
Right, like a dry heat.
Exactly. The WBGT index might only be in the low 80s because the wet bulb is dragging the average down.
Yes.
Conversely, if it is only 84 degrees outside, but it just rained and the sun is baking the wet asphalt, pushing the humidity to the absolute limit.
The WBGT could easily spike into the 90s.
Wow.
Exactly.
Yeah.
The WBGT is a composite index of physiological strain. It represents the heat stress index, which is fundamentally a ratio.
A ratio of what?
It is the ratio of the evaporative cooling your body needs to maintain 90.6 degrees, divided by the maximum evaporative cooling the environment will allow you to achieve.
Oh, that's brilliant.
And if that ratio exceeds 1.0, you're entering a state of uncompensable heat stress. Your core temperature has literally no choice but to rise.
Okay, so that formula works perfectly if the worker is, like, a statue standing in one specific microclimate all day. But a job site is chaotic.
Very.
A worker might spend an hour doing heavy lifting in the sun, retreat to an air-conditioned trailer for a meeting, and then spend 3 hours doing moderate work near a hot generator. We can't just take a single WBGT reading at 8 a.m. and declare the day safe.
You absolutely cannot. The physiological strain accumulates over time.
So how do we track it?
To manage this reality, safety professionals must calculate a time-weighted average, or TWA, of the worker's exposure over the entire 8-hour shift.
The concept of a TWA is brilliant. Instead of focusing on the arithmetic of multiplying minutes by temperatures, let's focus on the impact.
Okay.
It means that extreme environments disproportionately pull the average toward danger.
Oh, definitely.
Even if a worker spends 6 hours in a totally comfortable 74-degree WBGT zone, spending just 2 hours in an extreme 88-degree WBGT zone mathematically drags their entire 8-hour exposure average significantly higher.
Yes, and potentially crossing the threshold of danger.
And that threshold is strictly defined, right?
Very strictly. We compare the worker's time-weighted average against the permissible heat exposure threshold limit values, or TLVs, established by organizations like the ACGIH.
Right. And the TLV table is basically a matrix. It cross-references the worker's metabolic workload against their work-rest schedule.
Right.
Let's dissect workload for a second, because moderate and heavy are very subjective terms. What I consider heavy work, a seasoned iron worker might consider a light warm-up. How do we quantify this?
That's a great point. Safety science removes the subjectivity by looking at the metabolic rate, often measured in watts or kilocalories per hour.
Back to the fleshy light bulb.
Exactly. Light work is sitting or standing with minimal arm movement like operating a control panel. Moderate work involves sustained walking, lifting lighter objects, or maybe pushing carts.
And heavy work.
Heavy work is intense. Continuous exertion. Swinging a sledgehammer, manually shoveling dense material, dragging heavy cables. The heavier the work, the more internal metabolic heat the engine generates.
And therefore, the lower the environmental heat it can tolerate.
Precisely.
So let's look at the matrix. If a worker is performing continuous heavy work, the TLV table puts a hard stop at a WBGT of 25 degrees Celsius, which is roughly 77 degrees Fahrenheit.
Yep.
That is shockingly low. I mean, if the index hits 78, continuous heavy labor must cease.
It seems low until you remember the 1,000-watt internal furnace the worker's running.
Right, the engine is redlining.
The environment has to be cool enough to aggressively suck that massive heat load away. But here's the power of administrative controls. A safety manager doesn't necessarily have to stop the job. They can alter the time variable.
The work-rest cycles.
Yes. If you shift that heavy work from a continuous schedule to a cycle of 25% work and 75% rest, meaning the worker swings the hammer for 15 minutes and rests in a shaded area for 45 minutes.
Wow, that's a lot of rest.
It is. But their body is granted the time to flush the internal heat. And because of that, the permissible WBGT limit for that task skyrockets from 77 degrees Fahrenheit all the way up to 86 degrees Fahrenheit.
That's incredible. You basically manipulate the time to defeat the temperature.
Exactly.
But wait, I have a massive problem with this universal matrix. These numbers, 77 degrees, 86 degrees, they must assume a baseline, right?
They do.
What if I am sending an emergency responder to a chemical spill in August, and they are wearing a fully encapsulated level A hazmat suit?
Well, that changes the entire mathematical landscape.
I would imagine.
The baseline TLVs assume a physically fit, acclimatized worker wearing light summer clothing, like a single layer of breathable cotton that allows sweat to freely evaporate. When you introduce heavy protective gear, you are fundamentally altering the thermal exchange mechanisms.
Because if a worker puts on a vapor barrier suit, you have essentially destroyed that 70% wet bulb advantage. The sweat cannot evaporate into the atmosphere. It hits the plastic inside of the suit and just stops.
You've created a hostile microclimate.
A greenhouse.
The worker is trapped in their own personal greenhouse.
Yeah.
In these scenarios, the standard WBGT index completely fails to represent the true hazard.
So what do you do?
Safety professionals must apply mathematical clothing correction values. They literally subtract degrees from the permissible limit.
Oh, wow. Like a penalty.
Exactly. For a double-layer woven suit, you might subtract 5 degrees. For an impermeable vapor barrier suit, you subtract 20 degrees or more.
20 degrees?
Yep. A worker in a hazmat suit might reach their fatal thermal limit in just 15 minutes, even if the ambient weather outside seems perfectly pleasant.
That is wild. You mentioned the word acclimatized a moment ago, too, and that feels like a crucial biological variable. Does the body actually alter its own engineering to handle heat?
It does, and it is a phenomenal physiological adaptation. If you take a worker from a cool climate and drop them into a hot environment, they will suffer immense physiological strain.
Like day one on the job.
Right. But if you slowly expose them to the heat over 7 to 14 days, the body literally rewires its cooling system.
What actually changes inside the engine?
Several things. Blood plasma volume expands, providing a larger fluid reservoir for sweating and for cardiovascular transport.
Oh, so more coolant.
Basically. The heart rate decreases for a given workload. And most importantly, the sweat glands become hyper-efficient.
How so?
An acclimatized worker actually begins sweating at a lower core temperature. They sweat more profusely, and the sweat itself becomes more dilute.
Dilute, like less salty?
Yes. The body actively reabsorbs sodium and electrolytes to prevent cramping.
That is so smart. So a seasoned, acclimatized worker is physiologically a completely different machine than a new hire on day one.
They really are.
But even the best machine breaks if the parameters are exceeded. When these calculated limits are breached, this ceases to be a theoretical discussion about thermodynamics, and it immediately becomes a severe medical trauma.
Absolutely.
Let's trace the physiological cascade of failure when the heat overwhelms the human body.
So the failure usually progresses through specific stages, beginning with localized issues and escalating to systemic collapse. It often begins with heat rash, also known as miliaria rubra.
Right, and that's not just a rash, is it?
No, it is more than just an irritation. It is a mechanical failure. Prolonged, unevaporated sweat physically macerates the skin, swelling and clogging the sweat ducts.
Ouch.
The sweat is trapped beneath the skin, causing severe inflammation.
So it's basically the body's cooling vents becoming literally blocked.
That's a perfect analogy.
What happens next if they stay in the heat?
We typically see heat cramps. These are violent, painful muscle spasms in the arms, legs, or abdomen.
Like a Charlie horse, but worse.
Much worse. Physiologically, this is driven by massive electrolyte depletion. As the worker sweats out sodium, chloride, and potassium, the electrical gradients required for muscle fibers to relax are totally disrupted.
So the muscles just seize up.
Exactly.
The engine is running out of vital fluids. If the exposure continues, we move into a really dangerous systemic phase, right? Heat exhaustion.
Yeah, heat exhaustion is a state of severe cardiovascular strain and hypovolemia, which means low blood volume.
Because they've sweat it all out.
Right. The body is desperately trying to do two things at once. Pump blood to the working muscles to perform the job, and pump massive amounts of blood to the skin surface to radiate heat away.
It is a fluid distribution crisis.
Yes. The blood vessels at the surface dilate aggressively. And because so much fluid has been lost to sweat, this massive vasodilation causes blood pressure to just plummet.
Oh, so the blood isn't getting to the brain.
Exactly. The brain is suddenly deprived of adequate oxygen and glucose. The worker will experience dizziness, crushing headaches, nausea, and profound weakness.
And what do they look like at this stage?
Their skin is typically pale, cold, and clammy because the body is still desperately trying to sweat.
Okay, this is the final warning bell. Because if they push through heat exhaustion, they cross a physiological point of no return.
They enter heat stroke.
And that's the big one.
This is a catastrophic, life-threatening medical emergency. The thermoregulatory center in the brain's hypothalamus completely fails.
The thermostat breaks.
It shatters. The body realizes it is critically low on fluid and blood pressure, so it makes a desperate choice to preserve the vital organs. It shuts down the sweat glands.
Sweating stops entirely.
Anhidrosis. The skin becomes hot, dry, and flushed red. And without evaporative cooling, the core temperature just skyrockets.
The blueprint specifies a hard red line here. A worker's deep body temperature must never exceed 38.5 degrees Celsius or 101.3 degrees Fahrenheit. If it crosses that line, they must be pulled from the environment immediately. Why is 38.5 the magic number?
Because above that temperature, cellular destruction accelerates rapidly.
The denaturing we talked about.
Yes. The proteins denature. The cells of the intestinal lining actually begin to break down, leaking endotoxins right into the bloodstream, triggering systemic inflammation.
Oh my God.
Muscle tissue begins to undergo necrosis rhabdomyolysis, flooding the kidneys with dead muscle proteins, which can cause acute renal failure.
It's cascading failure.
Total cascading failure. The brain swells, leading to confusion, delirium, seizures, coma, and ultimately death.
It is a terrifying sequence. But the controls we use to prevent this cascade offer some incredible, almost counterintuitive physics.
They do.
Let's look at the 104-degree paradox mentioned in the environmental safety protocols regarding the use of fans.
I love this one.
We discussed how fans accelerate convective heat loss. But what happens if the ambient air is 104 degrees Fahrenheit?
Right, so this is a scenario that really tests a safety manager's understanding of thermodynamics. If the air is 104 degrees, it is significantly hotter than the worker's 98.6 degree core temperature.
Right.
So, according to the physics of convection, turning on a fan should blast hotter air onto the worker, transferring heat into their body.
You are essentially putting them in a convection oven. Instinct just screams that turning on the fan will cook them faster.
It does.
But the physics dictates that the overall thermal stress is actually reduced. How does the fan cool them while simultaneously blowing hot air on them?
It is a battle between convection and evaporation.
Okay.
The fan does indeed increase convective heat gain. You are blowing hot air on them. But that high-velocity air also aggressively strips away the saturated boundary layer of moisture over the skin, dramatically accelerating the evaporation of sweat.
And evaporation is the superpower.
Exactly. And because the latent heat of vaporization, the cooling power of phase change, is phenomenally stronger than the convective heat transfer of the air, the massive evaporative cooling easily overpowers the convective heating.
That is wild. The physics of phase change literally bullies the physics of fluid dynamics.
It really does. The net result is a cooler worker.
Provided they have sweat to evaporate, of course.
Yes, which is a big if.
Which brings us to the most critical administrative control: hydration. The protocols do not simply say, provide water. The physiological mechanism dictates the method. The guidance specifically requires workers to drink small amounts of water roughly every 20 minutes.
Yes.
Why the specific interval? I mean, if I am thirsty at lunch, why can't I just chug a liter of cold water to catch up?
Because the human gastrointestinal tract is a biological bottleneck.
How so?
The stomach can only empty fluid into the intestines, which is where it is actually absorbed into the bloodstream, at a maximum rate of about 1 to 1.5 liters per hour.
So it's like a funnel. You can pour a gallon into the top, but it's only going to drip out the bottom at a fixed rate.
Exactly. If a dehydrated worker chugs a massive volume of water, the majority of it just sits there pooling in their stomach.
Ugh, that sounds awful.
It causes painful cramping, sloshing, and nausea, and it does absolutely nothing to immediately restore their blood volume or sweating capacity.
It's the difference between a flash flood on dry, cracked earth versus a drip irrigation system.
That's a great visual.
The flash flood just runs off the surface, the soil can't absorb it. But drip irrigation provides a slow, methodical infusion that the biological system can actually process and distribute.
Exactly. Small, frequent intakes ensure a continuous supply of fluid matching that gastric emptying rate.
Perfect.
And beyond hydration, the controls demand a really comprehensive cultural approach. Permitting self-limitation is crucial.
Oh, 100%.
You have to train workers to recognize their physiological limits and empower them to stop work without fear of reprisal.
Which requires dismantling the whole macho tough guy culture that pervades so many heavy industries.
It does.
You cannot tough your way out of thermodynamics. Your proteins will denature regardless of your willpower.
They absolutely will. We also have to monitor workers on medications. Many over-the-counter antihistamines or blood pressure meds fundamentally suppress the sweating mechanism or alter cardiovascular responses.
Which would dramatically lower a worker's heat tolerance.
Dramatically. The safety manager has to manage the total biological picture.
Okay, so we have spent a significant amount of time sweating the details on heat. Pun intended.
Right.
But Domain 1 Topic 6 is a double-edged sword. We need to flip the absolute temperature scale and explore what happens when the environment stops trying to cook the engine and instead tries to extract every joule of energy from it.
The cold.
The physics of cold stress.
When we pivot to cold stress, our primary thermodynamic enemy shifts. Evaporation takes a backseat. We are now battling aggressive, conductive, and convective heat loss.
And the most prominent metric used to calculate this threat is the wind chill index.
Yes.
Every morning, news viewer knows the phrase wind chill. The weatherman says it is 15 degrees outside, but the wind chill makes it feel like -5.
Right.
But in a rigorous safety context, wind chill is not a subjective metric of comfort. It is not about what it feels like. It is a precise calculation of thermal extraction.
It is. The modern wind chill index is a complex regression equation derived from clinical trials, measuring the exact rate of heat loss from human skin.
It calculates how rapidly the combination of ambient temperature and wind velocity is draining that thermal bank account.
Exactly.
I want to look closely at the math behind this index without getting bogged down in the arithmetic, because there is a really profound physics lesson hidden in the exponent.
The velocity exponent.
Right. The formula includes the wind velocity raised to the power of 0.16. What does a 0.16 exponent actually represent in the real world?
It represents the nonlinear destruction of your thermal boundary layer.
A thermal blanket.
Yes. As we discussed earlier, your body naturally warms a microscopic layer of still air directly resting on your skin. That dead air acts as a crucial, invisible insulator.
So what does the wind do?
When the wind begins to blow, even slightly, going from calm to just 5 or 10 miles per hour, it violently strips that protective blanket away.
Oh, wow.
The initial heat loss is catastrophic. But once that boundary layer is gone, the skin is fully exposed. If the wind then increases from 20 miles per hour to 30 or 40 miles per hour, the rate of heat loss continues to worsen, but the acceleration of that loss flattens out.
So the first few miles per hour do the vast majority of the damage by stealing the insulation.
Yes.
Going from 5 to 15 MUVR is vastly more dangerous than going from 30 to 40. That is what the nonlinear math models.
Precisely. The equation mathematically proves that even a light breeze in sub-freezing temperatures radically shifts the physiological timeline to frostbite.
And just like heat stress, cold stress manifests in a cascade of specific physiological failures, categorized broadly into systemic collapse and localized tissue destruction.
Right.
Let's start with the systemic collapse. Hypothermia. This is the whole body engine failing. It is officially defined as the core temperature dropping below 35 degrees Celsius or 95 degrees Fahrenheit.
Right. And when the core temperature begins to drop, the hypothalamus triggers immediate emergency protocols.
What's the first line of defense?
Extreme peripheral vasoconstriction. The blood vessels in the arms, legs, and skin just clamp shut, drastically reducing blood flow to the extremities.
The body decides it is willing to sacrifice the fingers and toes to keep the heart and brain warm.
It is a ruthless triage. The second defense is shivering thermogenesis. The brain commands the skeletal muscles to rapidly contract and relax.
It is a desperate attempt to generate metabolic heat.
Very desperate. Shivering can increase metabolic heat production by up to 500%, but it consumes massive amounts of glycogen, which is muscle sugar and oxygen.
So it is running the engine at redline just to stay warm.
Exactly.
But eventually the fuel runs out.
And when the glycogen depletes, the shivering stops.
Oh.
This is the critical turning point in hypothermia.
Because the heat generation is gone.
Without that metabolic heat generation, the core temperature plummets. Neurological function decays rapidly. The worker experiences profound apathy, confusion, and lethargy.
Amen.
As the temperature drops further, cardiac arrhythmias develop, leading to ventricular fibrillation and death.
But long before the systemic engine fails, the localized damage begins, largely because of that ruthless circulatory triage we mentioned.
Yes, sacrificing the limbs.
The body cuts off the warm blood to the extremities. This leads to the most famous cold injury, frostbite.
Frostbite is literal mechanical tissue destruction. and it only occurs at ambient temperatures below freezing.
Because it's about ice, right?
Exactly. Because the blood supply is restricted, the temperature of the tissue in the fingers, toes, nose, or ears drops below 32 degrees Fahrenheit. And the interstitial fluid, the water between the cells, actually freezes.
And when water freezes, it expands.
It expands and forms sharp ice crystals. These expanding crystals physically puncture and tear the cell membranes apart, causing irreversible cell death.
It's microscopic shrapnel.
Basically.
Right.
When the tissue is eventually thawed, the destruction becomes apparent, often leading to gangrene and amputation.
But Domain 1 Topic 6 also highlights a class of injuries that I think surprises many people. Non-freezing cold injuries. You can suffer severe permanent tissue damage even if the temperature never drops below 40 or 50 degrees Fahrenheit.
The primary example of this is trench foot.
Right, from World War I.
The name originates from the horrific conditions of World War I, yeah, but it is highly relevant today for workers in flooded excavations, agriculture, or marine environments.
How does it happen?
Trench foot occurs from prolonged exposure to conditions that are wet and cold, but not freezing.
What is the mechanism of injury if there are no ice crystals puncturing the cells?
It is a slow suffocation of the tissue. Water is an incredible thermal conductor. It pulls heat away from the foot 25 times faster than air.
25 times?
Yeah, and the body responds to this continuous conductive heat loss with sustained vasoconstriction, clamping off the blood supply.
So the foot gets no blood?
Right. If the foot is kept wet and cold for hours or days, the continuous lack of oxygen and nutrients causes the nerves and blood vessels to die.
The tissue essentially starves to death.
Yes, leading to numbness, extreme pain, and necrosis, all without a single drop of tissue ever freezing.
That's horrifying. We also see chilblains, right? Which are painful inflammations of the small blood vessels in the skin caused by repeated exposure to damp, cold air.
Yep, chilblains are very common.
And there is even a physiological allergy mentioned, cold urticaria.
Cold urticaria is a fascinating immune response. When exposed to cold air or cold water, the mast cells in the worker's skin incorrectly identify the temperature drop as a pathogen.
Like a virus.
Exactly. And they release massive amounts of histamine, causing hives, severe itching, and in extreme cases, anaphylaxis.
Just from being cold.
Just from the cold.
So how do we engineer controls against the spectrum of cold hazards? With heat, we try to maximize evaporation and convection. With cold, we must construct a fortress against them.
The primary control is clothing, but not just any clothing. It is about understanding the physics of insulation.
Right.
The goal is to recreate and protect that thermal boundary layer of dead air.
Because static trapped air is one of the best thermal insulators on the planet.
Exactly. Safety professionals evaluate clothing assemblies using a unit called the clawlow, and layering is critical.
You can't just wear one big coat.
No, you need an inner wicking layer to pull moisture away from the skin, because if sweat accumulates, it becomes a conductive bridge that steals heat.
Right. Water conducts heat 25 times faster.
Exactly. Then you need a middle insulating layer, like fleece or wool, which is designed with millions of microscopic pockets to trap dead air.
The thermal blanket layer.
Yes, and you need an outer impermeable shell to block the convective force of the wind and prevent the trapped air from being displaced.
It is a really delicate balance of materials engineering, isn't it? If you wear too much insulation, the worker overheats from their own metabolic exertion, sweats heavily, the insulation gets wet, and they plummet into hypothermia when they stop moving.
Which is why the math of environmental safety is a continuous, dynamic audit.
We have mapped an incredible thermodynamic landscape today. We started by breaking down the core principles of human homeostasis and the continuous battle of thermal exchange.
The vibrating molecules of conduction, the fluid dynamics of convection.
Right, the electromagnetic waves of radiation and the phase change superpower of evaporation.
We examine the specific instruments designed to measure these forces too, exploring why absolute temperature scales like Rankine are necessary for physical equations.
And how to track the fatal limit of the dew point on a psychrometric chart.
We took a rigorous masterclass in the WBGT formula, proving why the wet bulb commands a dominating 70% of the calculation due to the physics of sweat.
We explored the reality of time-weighted averages, navigating the ACGIH matrix of work-rest cycles, metabolic workloads, and the critical mathematical corrections required when wearing impermeable hazmat suits.
and we track the physiological consequences of failure across both extremes. The biological cascade, from blocked sweat ducts and heat rash, through the cardiovascular crisis of heat exhaustion, to the terrifying cellular destruction of heat stroke at a core temperature of 38.5 degrees Celsius.
And on the cold side, the nonlinear physics of the wind chill stripping away our thermal boundary layer, triggering the ischemic starvation of trench foot and the crystalline destruction of frostbite.
It's a lot of ways for the engine to fail.
It really is. The ultimate takeaway for you as a safety professional is that environmental hazard management is not about looking at a weather app and making a subjective guess.
Not at all.
It is a precise, unforgiving application of physics, thermodynamics, and human biology. It is quantifiable math that literally determines if a worker comes home at the end of their shift. But before we close this session, I want to pose a question that bridges these established formulas with the reality of our future.
The changing climate.
Exactly. It is the unavoidable variable of a changing global climate. As baseline ambient temperatures steadily rise worldwide, and as prolonged extreme weather anomalies like stagnant heat domes and fractured polar vortexes become standard seasonal events, we have to look critically at the math we rely on today.
We really do. The ACGIH TLV matrices and the work rest cycles we discussed were developed based on historical climatic data and historical physiological baselines.
Right. But if the daily ambient WBGT in certain regions begins to permanently hover near the upper limits of human tolerance, will a cycle of 25% work and 75% rest even be biologically sufficient?
That is the existential question for occupational safety right now. If the environmental capacity for evaporative cooling is consistently overwhelmed by higher humidity and relentless radiant heat, the historical speed limits for the human engine may no longer apply.
The math might break.
The safety profession might soon face the monumental task of entirely recalibrating the fundamental mathematics of human survival to adapt to an unprecedented new climate reality.
The laws of thermodynamics are non-negotiable. We are the ones who will have to adapt. Thank you for joining us as we unpack the deep physics and physiology of environmental extremes. That wraps up this session of QHSE Talks. Keep challenging your assumptions, respect the math, and stay safe out there.